I'm very happy to see all of you today after yesterday's coffee breaks and great dinner. So let us start today the last session of this conference, and we're going to start with the talk given by Natalia Țânțaru on unlocking the power on electrospark alloying and electrochemical methods for shaping innovative materials. So please, Natalia.
So hello everyone, and I'm really joy to see everybody here. Yeah, please. You're welcome. So hope everybody is fine after yesterday's dinner, and today I'll talk about electrospark methods and electrochemical methods developed in our institute and our laboratory. So yeah, I represent two institutions from Institute of Applied Physics, Moldova State University, and Vilnius University. So, but before to dig in the scientific results, I again repeat that we are celebrating this year 60 years of our institute, and maybe this milestone it's not a big deal for very old institutions like Vilnius University, Catholic University, but for our Moldova it was a big achievement and to build this institution, because this institution is I mean, really famous, should I say, myself in the country, and not only, because a lot of collaboration, international collaboration. We have the lead publication of Moldovan scientists, so mostly 40% of this publication are published by our institute. We have our biennial conference, which is also famous in the country, not only, and we keep it during all these years. And I think in my more than 20 career of scientific research, I saw practically all of them. And also this year, we had, because of our achievements, received a plaque of excellence in research from the Academy of Science of Moldova. So again, attesting our achievements in the scientific field. Also, already in the first day of the conference it was mentioned, but I again say that So they're trying, but still should be some achievements made. And here I just explained that, this score is increasing during the years, so it's good for European Union. But if we look on the graph with other strong innovators like South Korea, and South Korea is a leading now innovator over the world, followed by Canada, United States, Australia. So European Union is not doing, it's doing okay, should I say, and as I said, its impact in innovation is increasing. Strangely, Japan has a little bit of decrease in this case, but what I was mentioned here also, that for the first time, European Union also was made evaluation of Moldova. And Moldova, because maybe we are trying to achieve to enter in European Union, and Moldova has some modest results for now, but still it's around this era, around South Africa, but okay. So, and there's some strong points that we have, and namely exports of medium and high technology products, SME, introduction business, process innovation, and public and private co-publication. What is the rule? But some decrease we have in environment-related technologies, employment in innovative enterprises, but also, unfortunately, decrease in the foreign doctoral students, overall of doctoral students present in Moldova. So probably some improvements can be made in these fields. So, and now I will switch already to more to our topic to innovation materials specifically. So innovation is not only about creating or developing new, also it's about improvement of existing products. And innovation of which we are producing mainly the laboratory coatings, different type of coatings. It's a vital role in improving you have a lot of equipment who is degraded, wearing. So in this case, for example, in situ technologies are very in demand now because European Union again demanding sustainability, energy saving. And in this case, materials obtained by electrospark alloying and electrochemical methods have been investigated a lot. So especially for coatings for corrosion and wear protection. And again, to a bit history, so the first director was also the first creator of this technology of electrospark alloying, but previously it was called electrodischarge treatment of surfaces. Why? Because there it was, Soviet Union, it was Russia. So in Russian it was more closely to electrodischarge treatment of surfaces. But over the world, it's called electrospark deposition or electrospark alloying. So in the literature, in scientific literature, you can see different type of terminology, but this is the same. And so Boris Lazarenko was founder of this technology and our first director. And in the end, this technology, it's about micro-arc welding process that use short duration electrical pulses to deposit electrode materials to a metallic surface. So here's a representative image on this. Just schematic I will show you what is happening inside. You have so-called tool electrode by which you manage to put some materials, metallic materials, It can be titanium, it can be different type of metals, and you have this workpiece working as a cathode, which need to be repaired over time, And it's made in the air, or it can be also made in the liquid. In the air, you have very good things. If you make in the air, you have a lot of nitrogen, So in this case, nitrogen also can enter in the coating. And like this, you can receive titanium nitrogen, what is very good. And very briefly to describe you what is inside of this process. So you have anode and cathode. And during these short pulses, you have a breakdown of interelectrode gap. After this, you have erosion holes formation with different type of zones. Here you see evaporation, melting, straight state, sorry. And after this, you have mass transfer between them when they have in the contact, short contact. And after this, you already have some deposited material on the cathode working piece and some material left from the tool electrode. So this method is quite versatile and it can be used for different very needed applications. So from dental and surgical instruments to dyes, punches, anti-gouling coatings, even for blades like this big. So, and of course, unfortunately, our big company Topaz, who was dealing with this, unfortunately doesn't exist anymore because of the war and all these difficulties started after the war. So, but the method itself is very unique, and it started by our institution, I mean, like Boris Lazarenko, but okay, he made a lot of things here also. Yeah, and advantages of this method, it's a strong metallurgical bond, it's practical no heat, even though there's short duration pulses, and mostly for majority application, you don't need it like big post-weld heat treatment. Substrate doesn't require a lot of preparation, applicable to most electrically conductive materials, efficient use of materials, environmentally friendly, because usually not have a lot of poisoning materials. Operators easily trained and applicable to complex shapes, of course not very complex, but okay. And by the way, it can be done manually, but also automatically. Of course, the speed will be different. And that's why limitation of these methods, it's relatively low deposition rate when we are speaking about manual deposition. Also high as deposited surface roughness, and some difficulties of composition and structure control, because when you are doing it manually, it's, yeah, can be tricky sometimes. And here I will introduce you a case study, the first case study, about wear resistance of cutting tools for sugar beet production. And this was made some time ago. I just want to remember this word because it was really efficient, practical, made in Professor Mikhailov group, led by him. So what is the idea behind? This was in this European project, it was with the acronym oil and sugar. There was problem of corrosion and wear resistance in sugar and oil production. And here you have these blades, yeah, which is cutting the sugar, I mean the beet, yeah. And these edges of these cutting tools are wearing very fast. Like after 10 hours, you need to reshape these tools, which is of course not convenient. And because if you not reshape it, you have already a different yield of sugar syrup, so which is not good, of course, for practical application and economically not convenient. In this case, in our lab, was specially made generator of electrical pulses, developed especially for this application, which was able to deposit a tin coating with high strength and reduced roughness, and composition you can see here. So it's mainly by tungsten, of course, and titanium carbides, which is, of course, a really hard material. And that's why, in the end, we obtained really nice results. Yeah. For example, you can achieve it like from 10 hours, we was able to achieve like 160 hours of work. So of course it was economically convenient result, yeah, and practical, yeah. So it's another process, but we, of course, our laboratory, it's not staying on the what it was done. It's going for new innovative decisions, should I say. And the new process was developed recently. It was published in last year in Coatings. So we decided to improve existing method by applying some extra. And this extra was very nice decision because here we have this tool electrode, we have working piece, but we also place it compartment for powders. And this is extended a lot of the use of this method because in this compartment you can put a non-metallic. Yeah, and this is, I mean, you already can manage to place different non-metallic materials and extend, and for example, to obtain multi-component coatings, composites, and control better properties. And they obtain very strong max phase. Which contained like carbides, of course, again, titanium, yeah, which I already mentioned. And it was nice results with a significant increase in productivity because you can increase also the speed of growing the coatings and service life, also the thickness. And here, briefly, I represent that, okay, this is where of this, for example, this is a substrate. Yeah, and this material is new obtained by this new method, and you can see that, of course, their resistance is much better. But, however, for example, in comparison with bimetallic systems, the corrosion of these coatings, it still needed to be improved, which our laboratory, I mean, they're improving this now. Working on this because nevertheless the wear resistant, it's very nice, but they are mostly porous, and we are working on stabilizing the regimes of these coatings and to make a better coating, yeah, more improved coating. And now I am switching to electrochemical methods. Why electrochemical methods? Of course, on our session yesterday, already we had some presentation about this, but I will speak about why it's. So it's relatively low cost, environmentally friendly method, because it don't have a high pressure, high temperature, whatever. It can be done on room temperature. Covering very complex surfaces can be coated. You can obtain high purity materials. I mean, everybody has computers with high purity electrodeposited copper. Yeah, and you can switch from very bulk materials with very high aspect ratio structures. For example, like this was obtained by me in cooperation with Carl Leuven and IMEC, these mini cookies. How we are told, yeah, so the idea behind here was to obtain a layer of cobalt tungsten between tin and pure copper in order to not make contact or contamination of copper by tin. So this was a really nice result. And also you can obtain even smaller objects like a nanovirus. In this case, it was electrodeposited cobalt nanovirus. And here also briefly, I want, without entering in details, you can, if you are interested, you can find them in publications. Here I just represent that, for example, we was able to achieve coatings with refractory metals like tungsten, molybdenum, and we are calling them for the first time ultra nanocrystalline wire. Because the crystalline size detected by XRD is very, very small. So to say it like 5 nanometers, 4 nanometers, I mean, it's really already tricky. And when we published it in Electrochemical Acta, of course, we made also TEM to show that, I mean, you cannot practically distinguish the nothing. So instead of call it like amorphous light, we call it this ultra nanocrystalline. And catalytic activity of these ultra nanocrystalline coatings, alloys, in this case, it's very high and applicable, for example, for electrocatalytic, also water splitting. If, for example, you are using also by our researchers, our group was developed also materials based on molybdenum sulfide, and also titanium oxide was mentioned yesterday. So we have a lot working in the electrochemical materials. Also, with our colleagues from Belarus, we developed knowledge-based deposition of very nice superlattices, which can be used for thermoelectric device fabrication. It was, why it's knowledge-based? Because they used wisely pulse deposition techniques, also under deposition techniques to create a very nice structure, developed structure of these superlattices. So also a good results, you can find more in our publications. And also mentioned by Henrikas a little bit in his plenary talk, we also developed during these years a very nice sensor of cobalt foam, electrodeposited cobalt foam. You see very developed structure which is allowed to increase the signal, yeah, of chlorine detection, of free chlorine detection and water. And like this we can decrease, or control the chlorine in the water. Yeah? And here it's already more complex. I'll more dig in details here because I like personally this work. It was a whole PhD study of our former colleague, Alena Nikolenko, who is finished his master degree here at University of State of Moldova. After this, she transferred at Vilnius University. Very nice achieved PhD in 3 years. So for young researcher, it's possible to make a PhD in 3 years exactly. After this, she obtained postdoc, Marie Curie postdoc in Spain, and now she's working in a research center in Spain. So really nice achievement of her, and this is part of her results. So what I want to represent here, so by electrochemistry, you can develop a bus, electrolyte, and switch pH, only pH, all the other conditions is the same. And you can obtain, for example, tungsten-rich or iron-tungsten-rich alloys. And why it's important, for example, you can obtain different morphology of this, different structure for the same amount of tungsten by only switching temperature. And if we map all these characteristics which was studied, like hardness, thermal resistance, and so on. So, of course, tungsten-rich alloys has high hardness, has also high thermal resistance. For example, you see, like 10, 20 gigapascal, depending on the heat treatment. So, which is a nice results and also applicable for thermal application. Unfortunately, iron is, of course, corroded very fast. And you can see here the wear depth of this material is quite deep. But if you couple it with inert material, for example, like aluminum oxide, so you have diminish the wear depth, so increasing the wear resistance. Also, because of corrosion, of course, the corrosion resistance, it's very low. But not always bad, it's bad. Because you can apply for biomedical application, this material, yeah? Because if you make a stent from this material, and it will corrode with some speed, or you have capsulated material, and you can bring this material inside a specific place, because it's magnetic also. So after corrosion, you can release, smartly the material there. But also, which this year, it's not our publication, some Korean, I think it was, they obtained from iron tungsten, they developed also layer on top, graphene oxides and silicon, and obtained hydrophobic materials. But also with low tungsten, you can obtain the high recording medium because of the semi-soft character. And like closing, we decided, and this is the last work of our good colleague, friend, Professor Digusa, was published last year in Lubricants about hybrid coatings. When we coupled electrospark alloying with electrochemical metals. Why it's important? Because I said the electrospark deposition, it's very rough. So we had an innovative approach. Let's to couple them. And indeed, because of the micro-leveling power of nickel, yeah, which was able, as you can see here, for example, this is the roughness, initial roughness of electrospark coatings. After thin layer of nickel, already roughness is diminished, and even you grow even more, you diminish it even more, like 30%, you can switch it, I mean, you can decrease the roughness. So it was a good idea. Another good idea, it was for corrosion properties, because this thin layer, to be shortly, the smaller box, the better, yeah? So the smaller box you have here, yeah, so the corrosion resistance is better, yeah? So it's improving a lot the properties of this material. So like this, we was able to make a hybrid coating and have innovative approach for this, yeah? And in the summary, I want to introduce our special, because electrochemistry, I show you that electrochemistry is still vital. So it's a special issue led by us and Henrikas. So the deadline is still there. So if you or your colleague interested in publish it in this special issue of materials, please, you are welcome, because we have 2 places maybe with discount. So you are welcome to publish. And of course, my acknowledgement for our collaboration, young researchers, especially Ramona, Aliona, Edita, Modestas, our PhD students who was developed a lot of work, and I am grateful for that. Of course, collaboration with the United States, but not only. As I said, we are collaborating a lot. And of course, thank you for all my colleagues in the laboratory. Thank you for your attention and presence in this last day of the conference. Thank you for coming today. And of course, so I hope you enjoyed our conference and hope you to see next time, next edition of our conference. So thank you.
Thank you very much, Natalia, for a very nice talk. We have time for questions. We're perfectly on time, so please, who has questions on this presentation, raise your hand. We have an assistant running around, so yes, please.
Thank you. As I see, wear resistance, the measurement in electrospark alloying deposits, the mean roughness is over 1 micron. Is too hard to estimate wear resistance, and in my opinion, the coatings have to be polished prior measurements.
Yes, I mean it's a good point. Good point, but depending on the testing, yeah. So of course, if you are testing all the materials the same, but also using a big load, yeah, high load, so it's not a nano scale, yeah. So you are using a big load, and in this case, you are doing nothing on them. So I mean, it's only polishing them, so you can see the results. Sorry. A lot of talk. So yeah, it's when we are doing like nanometer scale measurements, it's really detrimental to have a really nice surface. But in this case, in this electrospark alloying, it's like this.
Thank you. Any more questions? Yes. Yeah.
I can speak loud.
No, it's okay. It's okay.
Then I will speak softly. Your first method looks like an additive manufacturing technique. how is the adhesion, how is the interface between what you deposit and your metal base? Are there any contamination problem? When you do it in air, is oxygen a problem? So several comments on this.
Okay. So no, the method has a very, which is advantages, which I mentioned. One of the advantages of this method, it's strong metallurgical bond created under these short pulses. Because you have really a strong mass transfer in the material, you have some diffusion layer between the substrate and the coating itself, but the material, it's really hard because you see it's using in cutting application. So it's not delaminating, yeah, it's staying there. And oxides creating by this method, depending on the conditions, of course, it's even working on good results, should I say, because they stabilize. You have, for example, titanium nitride, titanium oxygen, titanium oxide, so they are working together.
But you mentioned heat-affected zone to be minimal, but now you mentioned diffusion, so it should not be that minimal, or it depends on the scale.
Depends on the scale, and depends, for example, which I mentioned that you have affected zone, but it's spreading very fast in metal. It's spreading very fast in metal, and when you touch already the surface after several seconds, it's already it's normal temperature. So because of the short pulses, the heat is spreading very fast. You have this very fast transfer of mass and very strong bond. So that's why this method created by our first director is a really nice piece of work, should I say.
If there isn't any other question, I would like to ask you whether you think to build things three-dimensionally by using this additive.
Yeah, I mean, there can be some innovative approach for this. As I already showed you, we can put some extra material from some device, yeah, like powders, not metallic powders. And but of course, the main idea for this method it's protection. I mean, like a coating. I mean, like really 2D coating. Yeah. To obtain 3D. It can be, I mean, I think, depending, because if you are using manually this equipment, I mean, depending on you can grow more, you can grow less. So, yeah. But again, for which application, we need to think, I mean, because, yeah, depending on the application.
Thank you very much. One more last question. Thank you.
Okay. Thank you for this very nice talk. I have, in fact, two but very, very short questions.
Yeah.
The first being, you were showing that you can use powder as the source, and can you control the thickness, and if you can, what is the range in which you can control it?
So the usual thickness of electrospark coatings, it's comparable with electrochemistry, it's very thick. It's 100 microns, yeah? Yeah. And so the thickness can be controlled, I mean, because you are putting layer by layer, yeah, so you can control it, yeah? And so one of the advantages of this method, you can grow really thick coatings because they are usually used for application, protective application, yeah? So, yeah. Of course, it's not atomic microscope, so you cannot grow there like nanometers, like also in maybe by electrochemical methods, yeah? So, yeah, it's usually, I mean, for thick coatings, 100 micrometers and more. Yeah.
Thank you. And then I have my second super short question.
Yeah.
Is there any way to avoid oxygen?
We don't need it, I mean, especially to avoid it, but if yes, you can put this equipment in the inert gas, so yeah, there is no problem, and you can obtain. Also, there is a liquid, I mean, liquid technique for this method when you can already make different types of erosions depending on the liquid. So the method is really, I mean, popular in engineering, and sometimes you need to avoid oxygen. But sometimes, as I already told, for example, for titanium oxide, which it's or from molybdenum oxide, which is a solid lubricant itself. You don't need it to avoid it itself. I mean, it's a good thing that it is there. So, yeah.
Thank you.
Thank you.
Thank you very much. We have to move forward to the next presenter. And just a short announcement as we get the connection with our colleague who is in Greece now. We're going to have three talks in a row, 3 plenary sessions, and then we come to the closing session. Afterwards, we have the coffee outside these premises. Thank you. So the next talk will be given by Stefan Rimchuk, and it's going to be on PLD of high entropy alloys thin films, tailoring properties by gas phase plasma chemistry. Hello, Stefan. Can you hear us?
Yes, I can hear you.
Yes, the floor is yours, so go ahead.
Thank you. Can you confirm if you can see my screen?
Yes, everything okay.
Okay. First of all, I would like to thank the organizers, but especially to thank Sergio for inviting us to take part of the conference. It's a pity that this overlaps with a different conference, which I'm at right now, but maybe in the next time it will be some better synchronization so I can participate. Just to say that I'm really sad that I missed the nice conference party that you had yesterday. That's the whole point of this. So I will talk a little bit about post-laser deposition of high entropy alloys, but I highlighted two things here: high entropy alloys and gas phase plasma chemistry. So when we work, we never work alone. So this is a collaboration between multiple institutes in different countries. There's a big effort in understanding pulse laser deposition, but not only understanding pulse laser deposition, but bending to our this technique to our needs for the applications that we look for. Just a minute. Yeah, my screen froze, so I don't know if you can see. Okay, outline here, it's happening. So I'll talk a little bit about plasma diagnostics, but more importantly, why do we need to understand gas phase reaction in pulse laser deposition, and how do we transfer that to high entropy alloys? Just so I think to make myself clear, but my colleagues with their previous talks, and I think Peter will do a better job than me to explain why high entropy alloys are maybe a difficult nut to crack when it comes to producing high quality thin films. And then you have a complicated material and you go with a complicated technique, you need to do it step by step. So that's why we are here. So I will talk a little bit about the context of PLD and why is it complicated. It's complicated because you have to take into account many cross correlation, and you have the physical properties of the target, then you have the physical properties of the laser that produce a complicated non-stoichiometric high energy multi-ionized plasma, and then that gives you a high quality film. Sometimes it gives you good films, but then the properties of the film also depends on the properties of the substrate. And the plasma, it's also mediated by a gas. So this is really complicated. But because this is really complicated, what we would like in the end was, or what our goal would be, to have this automated, to use machine learning algorithm to feed in a project, in a program that can then tell us either the best deposition conditions or to do the deposition itself. So it will tailor all the parameters, knowing the history of deposition for that material. But as I said before, it's a really complicated process. So it's nice that we have now a lot of machine learning algorithm programs, but it's important to know what kind of information to feed it to the material. So what would be a relevant property for the plasma? Is it the temperature? Is this the kinetic energy? Is it the Debye length? We don't know. So this is why we do the plasma diagnostics before. So from a complicated approach to a good result of what machine learning has done. And I think one of the biggest success of this approach to material science have been high entropy alloys, where different structure have been proposed as stable. And this high entropy alloy are one of them, so they can contain 4 to 6 elements in different concentration. And what the reason why we're looking at this high entropy alloys is because we want to combine all the elements and to get something new, something better that will surpass the properties of all the alloys that we have before. So basically, if we have A plus B should equal birds. This is what we want. We want to put all the elements together and to get really nice properties. But it's really sensitive from a thermal point of view. We want to have the lattice distortion, the sluggish diffusion, and the cocktail effect. And this is all the parameters that we need to take into account when we are producing the films. So now we are, hopefully you will see this slide again and Peter will do a better job to do it, but we produce high entropy alloys for different range of application, but more importantly, for the most recent one that we do, we use it for microwave absorbers and for infrared absorbers. And the idea is to control well the stoichiometry, so we need to have the equal amount of the elements in the right phase, in the right orientation, which is, you will see, maybe a little bit too complicated. So how do we do that? And the way we do that, we look at the plasma first. So I put the goal, we want to do high entropy alloys, but how do we go about high entropy alloys if the plasma is already too complicated? And to show, maybe just to give you a flavor of how complicated this plasma is, I will give you some examples where some easy deposition turned into a headache, and then that headache turned into a nice application, because this is what's nice about science. So if you look here, this is the current as a this is the ionic current in the plasma. So you see you have really fast electrons traveling in front of the plasma, which will be at the front of the plume here. And then you have ions, which arrive with different time of arrival, which means they have different kinetic energy, which for laser-produced plasma means different ionization states. And the proof of concept that we have, we used on silver, and all our diagnostic tools comes into this angle distribution. So we have multiple ionization states in the plasma, and they have a different angular distribution. So it's important to know where to put the substrate when we do the deposition. If we put it off axis or in the main axis, different ions will interact with the substrate. We also looked at the kinetic energy, and what we found for at least for our system is that there's a good, there's a significant pressure, which is 0.5 to a range of pressures between 0.5 and 1 Pascal, where the argon or the gas that we have in the chamber becomes dominant, and because an active part of the deposition, which is something that people haven't looked at it before. And then when we try to paint the picture of how the silver plasma expansion in argon looks, it looks like this Mickey Mouse figure, as you can see here, which is also funny, but also tells us that we have the ionization of the argon as it goes to the substrate. So pulse by pulse, you will heat your substrate with an argon plasma, which then again will affect the properties of the film. And then if we change the argon with the oxygen, we can look at the oxidation, and we can check the oxidation with a simple Langmuir probe inside the plasma. just by seeing this modulated variation in the electron temperature this time. So electron temperature becomes important for the oxidation system, and this is something that we need to take into account later for more complicated systems. And we also looked optically, and this is just to show you that our approach to understanding positive laser deposition works. We also saw for the first time the silver oxide molecule in laser-produced plasma, which was important for us to prove that we can see the oxidation and molecule formation and destruction during the gas phase during the process. So it's complicated for silver, but because we also were material scientists at heart, we do all the analysis. So then by controlling the oxygen in the chamber, we can change the oxide state of the silver, we can change the morphology, and then we can put all that to good use for antimicrobial properties. And we can improve these antimicrobial properties by controlling the oxide phase on the film. And it started from the process, started from the deposition, understanding, producing the films, and then towards the application. And now this is a robust technology. Like this is something that we can scale up, we can transfer, because we understand anything about the production. Now, other gas phase reactions that if we're looking at, so let's say we take up a different system like manganese oxide, and then we look at the current looks a little bit different. But important thing to say, when the current is mostly negative, we know we have oxygen ions in the plasma, and this is something that we need to take into account. And then this is basically a little bit of a commercial for maybe for our diagnostic tools. We can produce these beautiful maps, which is angle and time resolved. This also tells you where you can put the substrate, how does the position of the substrate will be affected by the energy of the particles, and this is something that you can see here. This is the angle, the pressure, and the kinetic energy of the particle with the ion density as well. So this is for deposition of manganese oxide in different gases. And then we can go and look also at the more delicate plasma parameters like electron temperature, plasma potential, and thermal velocity. And I would like to point out that the values and the distributions look quite similar. So when we do manganese oxide, when we try to deposit manganese oxide in oxygen or in nitrogen, the plasma as the pure plasma parameters are similar. This is a signal that we need to pay attention to, because when we went and deposited the films, we actually found out that nitrogen doesn't go into the structure of the film, but we can produce pure phase MNO. And this was something that was a signal from the plasma. The plasma told us that it's the same, but then we can get really nice crystalline and well-oriented films. And we see that also from optical transmission. People have done calculations, and this is the manganese-rich case. This is the band gap that we can find for MNO, and this is the oxygen-rich case. So we can confirm well with other theoretical calculation. We perform X-ray diffraction to check the single-phase orientation. Also, where there's a possibility of epitaxial growth, but we need to check with cross-section TEM for these films. But definitely there's the MNO phase in our films, regardless of the gas. So this time the gas phase reaction didn't do what we wanted. And maybe something more spectacular, when we looked at the nickel oxide system, and you will see like nickel, manganese, silver, these are all elements that could appear at some point in the high entropy material, but especially nickel. But if we look at the nickel oxide system, we saw that actually nickel spreads towards the edges of the deposition. So in the center, we have less nickel, and the ions move to the side. So we can understand, so the point of all of this, we have a really complicated deposition system, but it's complicated even for simple elements. So the nickel oxide, we can get nice films for the nickel oxide, but we can also understand why. So for the gas phase reaction, if we're looking at if we're looking at argon, if we're looking at nitrogen, if we're looking at oxygen for the nickel oxide, we see the only effect that's relevant, it's on the oxygen part, where we can see for the metal ions energy, you see the acceleration. So if we put more oxygen in the nickel oxide system, it will not slow down the plasma, as it does happen with argon, as it does happen with nitrogen. It will accelerate, and then that will affect the properties of the film. And this is something that we know, and we can control further with this. And of course, I told you about the 1 Pascal region where the gas becomes active, and then we saw there's an acceleration of the plasma during the deposition. So nickel, it's special in a different way, but we understand it now better because of these our special way of looking at gas phase as gas phase reactions. And we can also estimate even more finer things like acceleration of the ions during their expansion. And you can see here that the acceleration becomes less and less dominant, and then it sort of finds a way of equilibrium for the ions in the plasma. So pulse laser deposition, it's not a simple plasma, it's a complicated one. But the fact that's complicated and the fact that has all these tweaks and high acceleration and energy in the plasma. And if I moved past through it because maybe, but we can talk about it later. The energies for the ions in the plasma are reaching hundreds of electron volts, and in some cases even kilo electron volts. So in terms of energy, it's a high energy plasma. And then our approach is to take all that knowledge of plasma diagnostics and to apply it to these high entropy alloys, with the hope that we can get really nice pure phase high entropy alloy. And we started from easier system. We looked at the magnet transpatering, because we do also magnet transpatering for the high entropy alloy. And when we looked at the magnet transpatering plasma, we saw 3 important features only by looking at the optical emission spectroscopy of the plasma. So we saw that there's a really nice distribution between elements as a function of the wavelength. We also saw that when we do the Boltzmann plot, we don't see any equilibrium, but what we see is that argon and some elements sort of put their placing together, so they find we will have partial equilibrium for specific elements. And the most intriguing one is that there's a red shift in the emission spectroscopy of argon line, which means the particles are slowed down during the expansion. But more importantly, there's no oxygen during the deposition. So all the trouble that we might have with the oxidation of the film doesn't occur during the deposition. And I think that that's an important thing to have, and proof that we actually did the plasma and we recorded. But we also did some calibration of the deposition with this optical emission spectroscopy. And what we managed to do is actually to show that for titanium, there is a significant problem. And there's an optimum where we don't lose titanium anymore. If we add more argon pressure, the film will be titanium deficient, which we saw from our previous experiments. But now we can see it from the optical emission spectroscopy. And there's, when we look at the density, there's obviously 2 discharge regimes, with the optimum being 2 Pascal of argon. And this is what we used for the deposition. And this is the, I'm getting closer to the end. I don't know how much do I have, maybe 5-10 minutes, but now we're talking about high entropy alloys. So we did a quick test for high entropy. and we tried two different fluences. Different fluences will mean different energies in the plasma for the ions as they help the growth. And then we tried also different temperatures to see which would be an optimum temperature for these films. And for these tests, at least for this particular one, we used vacuum, so 10 to minus 5. And we didn't see any microbes or nanostructuring of the film. The film seemed quite flat. Of course, you can see small clusters, which is specific for pulse laser deposition, especially for metals, but the films are flat, really flat, and we're really happy. So usually when you have a flat film like this with PLD, first thing is that you made a mistake and you have no film there, because it's known that PLD gives rougher films, and we test them, and we have these. This is how the amorphous films look, and this is how the at high temperature we start to see this BCC2 phase, which made us to believe that we are close to epitaxial growth. This is an optimistic assessment of the films, but what we found with PLD, and maybe this is because the plasma it's too complicated, because you have the high energy, and because it's not an equilibrium deposition technique, you can capture and you can freeze better the high entropy phase. And this is something that we applied later, and we did also the optical emission spectroscopy during the deposition for the films, and what we saw, it's actually confirmed the test that we did. So we saw here that with the distance, the plasma has this mostly cosine to the power n distribution, which is expected. The intensity with the distance, it's you see here some variation, but the ratio between elements is the same in every place of the plasma, which means even though it's a non-equilibrium system, the particles travel the same, travel like consistently, and they don't get sequentially at the substrate. And also to point out that the spectra also give us an idea of the fact that we have clusters and nanoparticles. I don't have a film here to show you, but when we do the deposition, we actually can see these metal nanoparticles flying away from the target, and it acts like a splash on the water. If you hit the water with your palm, the particles will go outside. So this is something similar that happens during the PLD. But the main difference here, if you remember the magnetron sputtering deposition, is the ratio between the lines. If in the magnetron sputtering case, the argon lines were dominant, and you could see really low lines of zirconium and all the elements with a lower ionization state than what we have here. Here we see it more dominant. So this is also give us a fact that the plasma is more energetic, and a more energetic plasma could give us better films. We also looked at the electron temperature, and here this time the plasma it's in equilibrium more or less, and the argon line has a blue shift. The blue shift in argon line means the opposite that's meant with the red shift, means argon passes by high energetic ions, and this leads to the blue shift. So this is something good that we know. But what was curious for us is that the electron density and the electron temperature, they had like a sort of a strange behavior. We expect normally with the addition of pressure, as you saw before, maybe some monotone, an increase, and then a saturation, or just a decrease. But actually we see that there's a turning point in the evolution close to 1 Pascal, where something changes in the plasma, and that means for us that maybe after 1 Pascal we have some changes in the films. yeah, then here again we confirmed for the deposited films, and we also test the temperature deposition, and we saw that above 500 we get the BCC phase. So there are chances for epitaxial growth. And to end on a maybe positive or promising note, we also tried the microwave absorption test for the films. So we're one step towards the application that we wanted, and the results were, to put it in the words, the specialist that we gave him, he didn't expect to see such big difference between the films. More importantly, he didn't expect to see such difference between films produced in so like close range of pressures. But when we looked at the variation of these of the values, are really consistent with what we saw here. I'll go back 2 slides, and there is an inflection point around 1 to 5 Pascal, where it seems like even this time the properties and the behavior of the films in the microwave spectra changes. So we are able to go full circle with our aimed application. We can produce the films, they are crystalline, but we can also alter the properties to improve their microwave absorption. And we know why, because it has changes in the electron density and the electron temperature in the plasma. So we put everything together to end it. And this is something we also looked how the gas changes the nature of the film. So with argon, we get mostly nanoparticles, while with oxygen and nitrogen, we get most these foam or cauliflower structure. And this is a really, really nice evolution of what happens with the oxygen this time. And I put this specifically at the end just because it's always nice to end with a pretty AFM picture if you have it. You can see the crystallization changes, but this time a better look shows us that actually the flat surfaces that we saw, they still have some really, really small nano structuring. And in the end, we get this really nice cauliflower oxides, high entropy oxides, which will further be used for other applications as well. And with this, I think I'm in time. And I'm not going to repeat what I said before, but maybe I will reinforce the idea that our approach to pulse laser deposition and in general to understand deposition technique is to start from the physics, to start from the basics, to start from what makes it special. And for laser, for PLD, it's the plasma that makes it special because you have this non-thermal, non-equilibrium, complicated process, but it leads to exceptional results. So our aim is to understand that, to bend it to our will, and to try to connect in the end the application or the let's say the targeted property on the film with what we find in the plasma. And I think we managed to do that. We managed to do that for simple system, but we also managed to do that for high entropy, which is promising. And I'm really hopeful that in 2 years, when there'll be the next conference, we can bring even more diagnostics about this high entropy plasma. I would also like to acknowledge financial support from several projects, but mainly this this SPS NATO project, for which the latter part of the presentation was for. Thank you all for your attention, and I'm looking forward for your questions.
Thank you, Stefan, for a very nice talk. So Stefan Eremchuk is the director of the stealth coatings based on 3D architectures of high entropy materials. That's the NATO projects. And I would like to address if anyone has some questions to this talk, to this very nice presentation. Just raise your hand, please. Thank you. Yes.
Very nice talk. Thank you. Usually, so during depositions,
so can you hear me?
Yes, yes, we can hear you.
Yes. Okay.
Usually, so during processes, we have some coverage of windows, of chamber windows. And how do you consider previously deposited films on spectra of recorded optical spectra?
We cleaned before every, especially when we do optical emission spectroscopy, we chemically clean the windows, and we also check the transmission of those windows. So we try to be to work as clean as possible, especially that we have like a multi-purpose chamber and we use it for different materials. But we're aware of that and we try to do it as much as possible. We also have, depending on the window, different windows have different, let's say, wears for them, so we know exactly let's say, the amount of depositions after which we need to perform the cleaning. But we're aware of that, and we manage this drawback. Yeah.
Thank you.
Thank you. Any other questions? No questions. Let's thank the speaker again. And,
thank you.
Thank you. I would like to invite Petr Hruška with the talk on characterization of lattice defects of high entropy alloys in films by positron annihilation spectroscopy.
Okay, so thank you for your introduction. I have to say it's my pleasure to have the very last presentation of this beautiful conference. I hope you will like it. Also, I would like to thank the previous speaker for a nice introduction for this presentation, since I would like to more deeply speak about the characterization of those high entropy alloy thin films. So you have already seen the slide that we are interested in our group about high entropy alloys. I would like to point out that this group of materials, it was many years, we said it's a relatively new group, but I think that after 20 years of the first concept, we should really abandon this label as a new group of material, but still interesting. And also the name of high entropy alloys, it's still being used, in my opinion, because it's the most attractive name. But I think that the more precise is the third term, which basically explains that we study materials which are based on multiple principal elements. We are actually not caring about the entropy of those materials at the moment. But still, we can expect those 4 interesting features in our films. The high entropy feature, the stabilization of single random solid solution, also the lattice distortions caused by different atomic sizes, sluggish diffusion, and definitely also the cocktail effect. If we want to mix, let's say, 5 elements together, we have plenty of options looking at the periodic table. So in our group, we focus on refractory elements, more specifically the 4th and 5th periodic group. And as you already also saw this slide, we do not focus as let's say 90% of material scientists in the bulk entropy alloys, but in a more versatile thin films, which provide a larger variability of microstructures and actually tuning of the structure and the properties of the films. Stefan, before me, he spoke both about the magnetron sputtering and also about the results on pulsed laser deposition. So let me focus more on the magnetron sputtering deposited films. And as you can see, we have already found some interesting applications of those films. Yes, Stefan mentioned the microwave absorbers. In my case, I think it's particularly interesting, this one application, the photocatalytic degradation of biomolecules, and also studying the radiation and corrosion resistance. But before I get to the results of our research, let me draw this triangle, because this describes the way how we are studying and describing those materials. We need to examine definitely their structure with all different methods. Also, it was found that it is a key component to know the oxidation properties of those films. And also, you cannot connect these two features without knowing the defect structures of that films. And for the study of defects, I would like to introduce you the method of positron annihilation spectroscopy. It's a well-established material science method. And in case you are not that familiar about it, let me just give you a brief introduction to that. As you probably know, the positron is an antiparticle of electrons, and we can effectively use it as a non-destructive probe in solid-state materials, because it's effectively repulsed to the regions with low positive charge density. So in the case of a defect-free material, the positron is in a delocalized state, and its wave function is spread across the crystal lattice with local maxima in the interstitial regions. And this is really spread across, let's say, 10 millions of atoms, delocalized state. But when there is, within these 10 millions of atoms, if there is any defect, any void, such as a vacancy, the positron almost instantly is localized and trapped within this vacancy, and all of its wave function, all of its density is localized inside. And the method which is sensitive to this behavior of positron, this trapping, is called the positron lifetime spectroscopy. The quantity is called the positron lifetimes. You can see it's relatively easily can be calculated. And the important thing there is that those lifetime components, the numbers, they are unique for each type of defect in the material. It's sort of a fingerprint of a defect. Also, the intensity of this lifetime component, it carries information about the concentration of the defect. And in order to get the full information about the defect structure inside, you can use the complementary method, which is called the Doppler broadening spectroscopy, which is basically, unlike the lifetime spectroscopy, it's sensitive to densities in the real space. The Doppler broadening spectroscopy is sensitive to distribution of electron momenta in reciprocal space, and therefore it's sensitive to chemical environment of the defect. So together you can effectively describe really the defect structure of your materials. However, this positron annihilation spectroscopy, it was originally designed for bulk materials, not for thin films. So in, let's say, again, the last 20, 25 years, new types of slow positron beams were developed. And either you can use the pulsed positron beams with an excellent time resolution to study the lifetime, or continuous positron beams to study the Doppler broadening spectroscopy and the energy variations of positrons. It enables you to study defects in thin films of thicknesses from, let's say, 1 nanometer to 1 micron. So now let's get to the results of our thin films deposited by magnetron sputtering. The first kind of result is what happened when we did the very basic deposition conditions and deposited the films of hafnium, niobium, tantalum, titanium, zirconium on an unheated substrate at the room temperature. The resulting structure has this morphology, and the TEM observation, it confirmed there is no long-range ordering of the atoms because of a low temperature of deposition. So we have just amorphous film with these clusters of atoms, and only ordering within the range of, let's say, 1.7 nanometers. That's the coherence length of these clusters. That means that the atoms, they lose coherence after the distance which is comparable with 5 unit cells of the crystalline material. However, from the position of the amorphous peak, you can see it correlates well with diffractions of a crystalline target. And it's really at the same number which corresponds to the same nearest neighbor distance. So this is already some indication that this amorphous phase can be eventually used in further studies. Yeah. Also, when we picked those elements like the hafnium, zirconium, and so on, they are really, really sensitive to ambient oxidation, which is very nicely visible on the XPS results. Here in the top line, you can always see the state of as deposited films with dominant oxide peaks. And to remove this oxide layer from the amorphous films, we had to profile it by argon sputtering for about 7 hours to remove from 200 to 300 nanometers of the top layer to finally uncover these metallic elements. At least in case of titanium, niobium, tantalum, we really reduced it to the metallic. In case of zirconium, hafnium, there was still some signal from oxide, so it really oxidizes deeply into the material. And to answer the question why it happened so deeply, in the case of these films, it was not just the chemistry that the composition means that it has to oxidize, but we needed to know the process, the mechanism of the oxidation, and for that we found quite useful using the positron lifetime spectroscopy. Quick repeat, if you look at the lifetimes, you observe basically the defect sizes, identify the defects. If you look at intensities, it correlates with their concentration. So you can see we found 2 components of smaller defects, which it's difficult to call them vacancies when you have amorphous structure, but let's say they are something like vacancies and something like large vacancy clusters. And it makes no sense for thin films to have larger defects near the substrate than at the surface. This is not how thin film, metallic films grow. So if we correlate these depths with oxidation, what's happening is that the film is has uniformly distributed defects, and this size increase in the vacancy clusters is actually a transition from an empty vacancy clusters to clusters which has inner surface covered with these oxides. So this is the mechanism of oxidation of amorphous films, and the responsible defect are vacancy clusters. So if we want to make more oxidation-resistant films, we need to get rid of those vacancy clusters. This is the next step forward. Also, if we want to produce the crystalline films, it's a good time to watch the phase diagram, which was calculated by Kalfat method. And you can see there are several options of crystalline phases which can be obtained at lower temperatures below 700 degrees. There is a dominant 2 intermetallic phases, the hexagonal and cubic one, while the black one, the black phase, that's the true high entropic phase which we would like to achieve. However, it occurs at the temperatures higher than 800 degrees, and to have equimolar, just single phase structure, you need to exceed the temperature of 1000 degrees. And that was a problem for our laboratory because the current maximum deposition temperature limit is up to 800. So we were in the intermetallic region. But still, we had two ways how to introduce temperature into our system, and we could do that either by increasing the deposition temperature and crystallize the films during the deposition, or to deposit amorphous film and then heat it up and recrystallize it after the deposition. And here you can see the resulting structures of the annealing and of the deposition at high temperatures. I think you can clearly see that both ways went to production of crystalline films. However, the more effective one is the red one, when we deposit immediately at a heated substrate. The phase analysis, it revealed that we obviously don't have single phase films. We have a mixture in the left case of those hexagonal and cubic phase. However, the high temperature deposition, it also introduced some fractions of the high entropy phase. Also, on the left, the annealing, it gives you a higher concentration of defects, smaller grains, let's say a lower quality of the films compared to the deposition of the films at increased temperature. If we have a look at the defects, in this case, I present the results of the second method of the Doppler broadening. But again, just a quick review, we observe two quantities. The S parameter, it's reflecting more or less the average defect size, and the diffusion length of positrons, it reflects their concentration. So in the first plot, you can see that if we go from the amorphous film with the really largest defects to the films deposited at high temperatures, we are tuning the defect structure. We are slowly removing the vacancy clusters to the limit where we have only vacancies present in our films. And also, by further increasing the temperature, we can even, by increasing the diffusion length, we can reduce their concentration. So the temperature, it allows us really to control which open structure we want to have in our films. And the impact of these different defect structures on the oxidation properties is demonstrated by this experiment. We needed to compare, let's say, or characterize the dynamics of this natural oxidation. So we compared XPS results of two types of samples. First one was normally exposed to the air, transported to the XPS apparatus within the time scale of 20-30 minutes. And the second type of samples, they were transported using the vacuum suitcase, so without exposition to ambient air. And here we compare the film which is amorphous, the one which should extensively oxidize, and the film which is nanocrystalline. And I have to say, nanocrystalline, but with still relatively large concentration of vacancies, but without vacancy clusters. And the results are well visible here. You can see that the nanocrystalline film, yes, it oxidizes on air, but the difference is negligible compared to the results for the amorphous film. So really, by controlling and removing those vacancy clusters, you can make your films resistant to the ambient oxidation. Since do we have time? I guess so. Also, we still had in mind to transform our films into the high entropy phase. And since we couldn't increase the temperature during the deposition, we tried to do it after it. And we believe that since this natural oxidation is relatively weak, we can achieve it. So we put it into a vacuum chamber. Actually, it was the apparatus for measurement of positron annihilation spectroscopy, and heated it up step by step up to the temperatures of 1,400 degrees. Well, the morphology, it looked promising. We really increased the grain size massively. Also, the final state was more or less the same in case of, or regardless, the initial state, if it was nanocrystalline or amorphous. But the phase analysis, it showed that we didn't actually obtain a single phase at all, but instead we got a mixture of oxides. And really, really complex oxides because there was a reaction at the surface with the residual oxygen in the vacuum, also a reaction with the oxygen from the magnesium oxide substrate. But still, we could monitor the changes during this annealing, again, by positron spectroscopy, and it is well visible here in the first picture that even at the 400 degrees temperature Celsius, we still have the magnesium oxide substrate. It's still intact, so it doesn't react at these lower temperatures, but at the surface regions, at these low implantation energies, it's already changing. So first, it reacts with the oxygen from the top, then it reacts from the oxygen from the bottom. So the magnesium oxide, yes, it is a problem if you want to post-process your films, but it will not ultimately save you from the oxidation problem. So we needed to get back. We had limitations of our deposition system. We had limitations also of our samples and their composition, but we still wanted to produce the single high entropy phase. So then we got an idea that instead of trying to get to the temperature of 1000 and more, let's probe the intermediate region of moderate temperatures and see what will happen. Maybe utilize this amorphous structure as a precursor for this high entropy phase. And I have to say we were successful in this matter. If we increase the deposition temperature by 100 degrees, it is still amorphous, but at 200 degrees, so we started to observe crystallization. At higher temperatures, we have already compact nanocrystalline film. Further increase goes to final crystallization of this fabric-like morphology. And when exceeding to the temperature of 600 degrees, you can see that this 500 degree structure was metastable and it dissolves at higher temperatures, and this is actually the transition to the crystallization of those intermetallics. The phase analysis, it confirmed this picture, that really the single cubic, base center cubic phase is emerging at the temperatures higher than 200 degrees. Just the grain size is relatively small, so we cannot achieve a large polycrystalline or epitaxial films, but we have single phase films. If we look at their oxidation properties, of course, there's again a dominant oxidation of hafnium and zirconium, and you can see if we always compare the state which is naturally as received with the one where we uncovered the top layer, you can see that the most oxygen is really bonded to hafnium, zirconium, titanium, while in case of tantalum and niobium, they can be uncovered to the metallic state relatively quickly. So observing the niobium and tantalum, it can give you information about the level of the oxidation, which I will use, let's say, in a minute or two. Also, the defect structures, they just confirmed our picture. We observed 3 types of defects besides the vacancies and some clusters which were present mainly in the case of the amorphous films. We observed some micropores, but with really low concentrations, really low intensities. And also we have seen that we are obviously improving the crystallinity of those films. We are reducing the average size of the defects. Also, we are reducing their concentration with increasing deposition temperature. So that means that the film at 500 degrees is a really good initial state for further studies. Now, at this point, I would like to introduce another way how to oxidize these films, because the first goal to produce the single-phase high entropy film, it was accomplished, but still we would like to also do some research on these high entropy oxide films. And as you've seen, we didn't achieve them yet. Increasing the temperature, direct oxidation, this doesn't lead to good results, but you can do it at room temperature in using electrochemical oxidation. Here I borrowed 3 nice pictures from the Berger's study, where he performed the anodization on the same composition of high entropy alloy on the bulk sample, and he obtained this nice oxide nanotube microstructure. So we got this same idea, we got the same composition of electrolyte, and we tried to electrochemically oxidize 2 samples. We needed one, so without some elemental separations, so we couldn't use the high temperature grown. We have to use either the amorphous film, which has short range order, but no separations of atoms, and also this nanocrystalline film, the finest one, and see if we can produce the high entropy oxides. So these are the results which were obtained by our Slovenian colleagues. On the left is the original amorphous film, on the right is the original nanocrystalline film, and this is the effect of electrochemical oxidation. You can see that it makes the similar morphology as was observed by the bulk studies. Also, the optical properties of this anodized area, this round region, they were much different, and when we characterized them, we observed, in case of the amorphous film, a single band gap, while in this region, you can see 2 colors, we observed 2 wider band gaps. The oxidation, as I said, it's interesting to study only the tantalum and niobium states. And just to resemble the effect, or compare the effect of natural oxidation and of the electrochemical oxidation, you can see that in the previous pictures, the argon sputtering, it removes the oxide layer in these 2 elements, and they should be present almost dominantly in the metallic state. While in the case of electrochemical oxidation, there is still dominant peaks in the oxide states. That means it is really more effective to put it into electrolyte and oxidize it by anodization than just expose it to air for a long time. And finally, this surge in high entropy oxides, it's motivated by the nice application. It's which can be called a photocatalytic degradation of antibiotics. It can be a procedure which you can use for wastewater treatment. And we did some first basic experiments on degradation of tetracycline. And the function of this high entropy oxide should be that it should that the tetracycline should be absorbed on these high entropy oxide, and then we have more time and higher efficiency to degrade it by UV irradiation. And as you can already see, just the pure illumination effect is the black curve, while the effect of the crystalline film, it's at the level of 20 to 30%, so it really can work in this type of application. So let's briefly conclude this presentation. I showed you the 3 types of thin films based on high entropy alloys with the amorphous structure, nanocrystalline structure with multiple and single phase. We correlated the results with defects and their oxidation properties, and we still have some job to do. The ultimate goal at the moment is to produce high entropy oxides. So let me thank all of my colleagues and the funders at the moment, and also thank you for your attention.
Thank you very much, Petr, for a very nice and interesting presentation. So the presentation is open for discussion, please. Who wants to ask questions? Just raise your hands. Yes.
Thank you for the very nice presentation. Regarding the diffusion of oxygen in amorphous versus crystalline, the common wisdom is that an amorphous structure will be a diffusion barrier better than a polycrystalline. However, what you've shown is different. Do you have an explanation?
Well, I didn't study the defect aspect of other amorphous structures, but if they are that open, I think that if you have an open network in the amorphous film, which is also covered with these Gettering atoms like hafnium, zirconium, it actually makes a path for deep oxidation. So, for example, let's say if I manage to do some iron-based high entropy alloy, which is not that susceptible to oxidation, maybe the amorphous phase would be more resistant than the nanocrystalline.
If you suspect that an open network, do you have data for the density of the two phases?
I don't. I just have the local information about the open spaces.
Okay. Any more questions? Yes, please.
When you show the sequence with different temperature for the crystallinity,
yeah.
At 500, my impression is that there is some texture there.
Yes.
Is that correct?
Yes, it is.
Any more questions? No? Okay, let's thank the speaker again for his very nice closing presentation. Thank you, Petr. Ladies and gentlemen, this very nice conference, the 10th conference on material science and condensed matter physics, is coming to its end. So I'm really happy to meet all of you here for this very nice talks, very nice discussions, nice conference dinner. I'd just like to, first of all, mention that we are in the Moldova State University right now, and the conference is fully supported by the rector of the university, Professor Sharov. And you know the conference chairman, academician Kuluk, conference secretary Nikita Semenel, myself as a co-chair of the conference, and program committee chair, academician Arushanov. On behalf of all of us, I'd like to thank you for taking part in this very nice, interesting event. I would like to come with some statistics on the conference. So we have 207 attendees, registered participants. We had 195 abstracts discussed in 6 sections, 2 workshops taking place at the same time, and we had 71 participants from abroad, Moldova, and the overall number of countries, I think, excluding Moldova, is 18, excluding Moldova. And what's the most important part is that all these talks are of high quality, as you can see today and the very first day and all the days during the conference. I'd like to announce that you're going to receive an email with which states a possibility of full article publications in the journal called Physics of the Solid State, and the editor of this journal is Professor Nika. So this will happen shortly after the conference comes to an end, I would say in a week or so. And I'd like to, before I come to the last words, I'd like to say that, of course, people are the most important part of the conference, right? So this conference wouldn't be possible if there would be some really nice people whom you maybe didn't see during the conference. They are always here, and they made it possible to get you from the airport and back, to have this always nice food, yeah, all the coffee breaks. And let me just, I would like to go through just to avoid excluding someone from the list, from the full list. So the conference is organized jointly by the Institute of Applied Physics, Scientific Association Material Science and Engineering, and the Faculty of Physics and Engineering. So if we go just by list, So special thanks to all the people who have been instrumental in this very nice event. And Olga Shikimaka, Alexei Mishalkin, very nice logistics, all the logistics of the conference done by him. Dorina Круитор, Mariana Roma, Nikolai Kormeyev, Oleg Reov, Sergei Островский, Natalia Kazak, Anatoly Semenel, Alexandru Miku, Valentin Batyr, Anatoly Kukharuk, Ирина Филиппова, Нина Юзва, Лилиана Дмитроглу, Наталья Недиоглу, Вадим Серкили, Аркадий Кирица, Дорин Спояла, Игорь Нарольский, Эльмира Ватаву, Георгий Гилецкий, Варзаль Александру, Влад Моисей, Ирина Майструк, Елена Берку, Татьяна Юрьева, Евгений Успеней, Lisa Moshняга, and Alexandra Belenchuk. And I would like to also bring a lot of thanks to the people who made it technically possible for this conference to take place. And I'd like to thank a lot our IT guy, Евгений Успеней. Please applaud him for his efforts, because we have now an online, we have all this recorded and placed online on YouTube and Facebook. And Drago Shunguryan and my students Viktor Bolf and Kristi Seinik also assisted. Maybe you didn't see them, but they were all the time around. And well, I think I didn't forget anyone, but I'd like to I'd like to ask for your applause for the lady who organized very well all our conference coffee breaks. Milana Semenel, please give an applause for. We're gonna. I think the conference, the coffee breaks are just outside, and we're gonna go right away for that. But so, just a few closing remarks, and I really want to see all of you here, and way more people coming from abroad for the very next conference, which is scheduled for 2 years from now. And yeah, I'm going to give the floor to Academician Kuluk for some concluding remarks.
Just few words. Just few words. First of all, the mission is successfully accomplished. It was not so simple. And once again, many thanks to all people that were involved in the organization of this conference. Anyway, after the finishing of such event, in the soul a void still remains, and is the reality. I hope that we will be able in 2 years to organize the next edition, and in 2 years we will have a possibility to meet here again at the 11th edition of the conference Material Science and Condensed Matter Physics. So see you soon. Thank you.
So by this we close a very nice conference, and everyone is expected for a nice coffee break. Thank all of you.